Who's going to be speaking on conditional hardness results for massive parallel computation from distributed lower bounds.
Okay, great. So, as the title suggests, I'm going to talk about exactly the same stuff as Sohail was talking about in the last two talks. But this is going to be a bit more negative in the sense that instead of nice algorithms for upper bounds, I'm going to at least try to convince you that not everything is easy. So the model is exactly the same as before. I'm not going to go too much into it. So we have these computers. We have an input graph. You split the input graph among the computers. Then the computers are connected into this communication network where everyone can talk to everyone. And we care about synchronous communication rounds. And we also care about these memory parameters in the system. So again, here we fix some memory per machine, and then we would like to have that the total memory in the system is roughly linear in the input size, which is the number of edges in the input graph. And now, opposed to the last talk, I'm focusing on this sublinear memory regime. And here I'm trying to show that you cannot solve the matching too fast. And here the crucial thing is that I cannot, at any point in time, store any sort of global overview of the graph, which kind of just means that, for example, any machine cannot even know the name of every node in the graph at any point in time. And kind of motivated by this, it's good perhaps to think about a bit how does the output of the system look like. So I cannot say that one machine is kind of responsible for eventually saying which edge is in the matching and which one is not. But actually, I'm going to require that in the beginning, the machine that gets assigned some edge in this division of the graph, this guy has to say in the end that my edges are either in the matching or not for every one of the edges separately. And yeah, I'm going to care about, again, this matching problem. It's not the maximal matching, but approximating the maximum matching. But actually, all of the stuff I'm saying also holds for these maximal matchings. So what's known so far? And again, trying to motivate a bit why I'm talking about this sublinear memory regime. Well, if we have superlinear memory, actually from the previous talk, you already heard that you can solve this problem in constant amount of rounds. And it's not the first work to show that. And then if you go to the linear memory regime, well, again, in the last talk, you saw how to get this thing done in log n rounds. But then if we go to this sublinear memory regime, then we have somehow much worse runtimes, and we can only get to something like square root of log n rounds. And here we don't, at the moment, really know if we can go down to this log n rounds or better or not. And I want to point out one paper that Sohail, I've been too long around Germans that always do this mapping of E and I. Anyway, so there is this result for sparse graphs where we can get down to polylog n rounds. And soon you will figure out why I'm mentioning and highlighting this result here. But it maybe gives a bit of hope that we could get down to this log n rounds also in the general case. So what we showed is that if we assume that there is no algorithm that works in sublogarithmic time for connectivity, then first of all, we get that you cannot solve this maximum matching approximation or maximal matching in log rounds. And just to kind of show that it's not only this result we got, but we kind of could use our technique for other stuff as well. We got a triple log n lower bound for the distributed Lovász local lemma problem. And we got this nice log of log star n lower bound for delta squared node coloring. And why I like this result is that it's a very meaningful lower bound in the sense that you cannot really come up with a number that makes any sense in this regime anymore. So I mean, if you put the number of atoms in the universe, it's still going to be something ridiculous. Okay, and now why I highlighted this one result that we had is that our lower bound for the matching actually also holds for trees. So we get this log n lower bound also for trees, and then this log cubed algorithm actually starts to sound like it's getting pretty close to the optimal. So probably we were doing something right here, and maybe this also hints again a bit to the direction that the log n might be the right answer for this problem. Okay, good. So now I'll try to explain the title a bit more and kind of give a very high overview of how our framework works. So the first thing we do is this conjecture, and it's basically the same thing as was mentioned before, that connectivity in this model is hard. And then we are going to take some lower bounds from a different world and somehow connect these two things. So we hook these two kind of different things together, and then from this we would hope to get lower bounds for this MPC model. And first, I want to say a few words about this conjectured hardness. And because you might ask, kind of like, okay, why are we doing conditional lower bounds in the first place? So like, are we just too lazy to do these things properly? Or is there actually some reason for it? And I claim that we have a reasonable reason to do this conditional workaround, which is that essentially, if we could come up with any sort of meaningful lower bounds for this MPC model, we would get some very strong results in circuit complexity. And maybe this is not a reason not to try at all, but I suppose that people might believe that it's at least a good excuse to go more modest to begin with. So let's just assume that we shouldn't try to do unconditional lower bounds for now. And then in this, I think it was the first talk, this conjecture was mentioned that it's difficult for these low memory MPC algorithms to distinguish one cycle from two cycles. And one thing we did was to kind of formulate this conjecture in a nicer way, and we kind of brought out a much, I don't know, it's not cleaner, but it's somehow much nicer problem to deal with. That it's still hard, and I mean, we showed that this problem is also hard if the two-cycle conjecture holds. And how does this problem look like? Well, essentially, your input is a set of paths, and all the lengths of the paths are fixed. So we can decide what is the length of every such path. And here, now you ask, like, are these nodes S and T on the same path or not? And if you can answer this question, you can also solve the two-cycle conjecture. So basically, we can focus on this problem instead of the less nice one for our hardness proofs. Okay, good. And that was about that. And then there are these locality lower bounds written on one of the boxes. And now I would like to explain what these things mean. So there is this nice model called the local model. And I guess that many of you were in the best paper session. And here the local model was introduced. So maybe you remember something from it. But the basic idea here is that you want to solve graph problems such that you take, let's say, a node, or an edge in our case for the matching, and this edge is allowed to look up to r rounds around it, and then it has to decide whether it's in the matching or not. And this may sound kind of trivial, but the crux is that you have to do this for all the edges in parallel. So every edge at the same time must decide whether it's in the matching or not by looking at their R-hop radius, the topology of the graph in their R-hop neighborhood. And this, sorry, and here when I say the locality of a problem, it just means what is this R? Like what is exactly the distance up to which you have to look at to solve any problem? So you need to look until this distance and at least that distance, and then we get this locality of some problem. Again, why all this hassle? Well, one of the reasons is that we know a lot of unconditional stuff here in this local model about these localities of some problems. So for example, for this matching approximation, we know that in the local model, you have to look at least up to square root of log n distance until you can solve this problem. And then now you see that these other problems that I mentioned pop up here as well. So we know stuff about this Lovász local lemma or this syncless orientation. There is an instance of it, node coloring. And in the best paper session, you saw a new result on maximal matching as well. But you can forget about the other stuff for now. So we are just going to discuss this matching approximation. And how can we use the locality of matching approximation to derive an MPC lower bound? All right, and I think it's good to go a bit more into detail. What does it actually mean that someone has to look far in the graph? And the basic idea is just that here, if you have this edge E, and I say that he has to look up to radius R, it means that you need to know the topology up to R hops. And in particular, it means that there is some node up to distance R whose existence you have to know. And I wrote here in this box that you need to know, or you depend on information in distance R. So what I mean by this information, on top of the topology, like the graph topology is kind of obvious type of information, but you also have something like unique identifiers on the nodes that you can learn up to that distance. And unique identifiers could also here stand for some random input string for the nodes, or you can just think of them as randomly chosen unique identifiers for the sake of this talk. But anyway, the take-home message is that if you have an edge E and I say that locality is R, then it means that there is some information in the graph far away from that the node or edge has to figure out before it can decide on its output. Good. And then from those, I would like to somehow hook these guys up to actually get my MPC lower bound. All right. So the first thing we showed was that if the locality of some problem is R, then also an MPC algorithm has to figure out some information in the graph in distance R. And I mean, this may sound kind of silly to even state after all the stuff I talked about before, but in this MPC model with all this all-to-all communication business, this becomes a bit more formal than one would maybe hope. Like even what does it mean to figure out some information in this MPC model is a bit less nice than in the local model. But let's just now take this for granted, and I'll show how to use it, because that's perhaps more exciting. And the idea is that imagine now that we have this graph where these nodes S and T are in the same component. Okay, now I have this previous statement that the locality of matching is R, and I somehow, this edge E has to figure out some information about T. So what the node T can do is that it can change the local information without telling the edge E about it. And to solve this problem, this edge E kind of has to see that some change happened. And now to make it a bit more explicit, imagine that the upper part is the real input to the problem. Now the node T can create a virtual graph and run the same algorithm in this virtual graph, and he knows that it should be the case that the output changes. So he knows kind of that in the original graph, the output is something, but in this virtual graph, at least with some reasonable probability, the output changes. And now in this MPC model, it's easy to repeat this process, so I can kind of do this test many times in parallel, and then you can change this probability lambda that I wrote there to basically be whatever probability you would like. So in this way, I can create a test where the node T can try to change its local output. It can try to change its local input, and if it sees a change in the output, it knows that the nodes are in the same component. So essentially, I created a test how I can figure out if I'm in the same component with this edge E. And then, if I have the case where they are in different components, at least intuitively, this test should fail. And, sorry. Okay, so if I do change the local input around T, then why should this edge E in another component care about that? And now one has to take my statements here with a grain of salt, because it's not really true what I'm now going to state. We had to cheat a bit to get around it, but basically we showed that if T changes the local input a bit and is in a different component, then we shouldn't see any change. So basically now what the T guy can do again is to create many copies of the graph where he changes the local input, and if he sees that no change happens in the graph, then I can figure out that we are in different components. All right, so what did I achieve now? I now have the means to try, or I have created this test where I can check if we are in the same component. I created a test how I can check if we are in different components, which then kind of concludes that I can check using a matching algorithm whether S and T are in the same component. So I use a matching algorithm, see if the outputs change, and then I can figure out if we are in the same component or not. All right, and that now there's not much more left to do. So the ingredients we have is this checker if we are in the same component. Then we know that the locality of matching is roughly the square root of log n. And now let's assume that we have a matching algorithm that works faster than log n rounds. And let's recall this nice problem that we conjectured to be hard. And here I can now set the distances, the lengths of the paths to be roughly this locality of the matching. And now I can use this checker in this graph to figure out if S and T are connected in time that is sublogarithmic in this distance, which is then sublogarithmic in the, I think I now said it twice. I can check with this matching algorithm in time sublogarithmic in the distance whether these guys are connected. And this is contradiction to the hardness assumption. All right, great. And then I just wanted to bring out the picture once more. So we use this conjecture that connectivity is hard. We applied these nice lower bounds we know from the local model of distributed computing. And from that, we were able to create this lower bound for the MPC model. And then I would just like to finish with some open questions. And I guess these were pretty much already posed in the earlier talks. But yes, it would be very nice to beat this square root of log n runtime for the matching in the sublinear memory regime. And actually, I may be even more excited about this maximal matching than the matching approximation, but that's a matter of taste. And then it would be also nice to beat this log n runtime from the previous talk, but I guess then there one would need to do something different than what we did so far, or what they did so far. And that's it.
Thank you.
You have this comment that this algorithm is assumed, that the behavior is assumed only to depend on vertices within the same connected component. And there are things that MPC algorithm can do, like counting the number of vertices, that are very plausible that don't have that property. So
yes.
That.
I was hoping that no one asks anything about that. So, well, I don't know what would be like a good answer that doesn't make me look like an idiot, and I don't know if there is one. But the real truth is that we couldn't get rid of this assumption. We wanted to, but we couldn't, so it stayed there. It would be nice to not have it, but I don't know how. Even when you look at the details, it might sometimes feel like, am I not now assuming that the conject or that the theorem holds and then proving it? But it's not trivial then if you start to think about it, but it may look a bit silly. Sorry, create what?
Is there a way to construct the two graphs geometric distribution?
Well, depends on what you mean by efficiently. I mean, here we don't really restrict the local computation power, so you don't really need to spend any time for that. So in that sense, efficiency is maybe not the problem, and I guess that even if you would think about copying, you just need to copy everything and say that you're in copy number 1 and the other one is in copy number 2. So I suppose that it's not difficult to do that efficiently.
Yeah.
Was the method mentioning sparse graph, the graph, is it log n squared or I thought it was?
It's cubed because there's one log delta factor, and I mean delta can be up to n. Huh? Is it squared? Really? Okay. Okay. I checked it at some point, and maybe I then corrected it wrong there. My bad.
All right. Any other questions?
Sorry, so you mentioned something about nodes not knowing other nodes' IDs or something. So are you assuming that nodes can't directly communicate with another node based on their ID? And does this assumption make a difference in your analysis?
Well, I guess that it wouldn't really help even if you would somehow have a magic address book with all the IDs of the nodes, but yeah, I don't know if it makes a difference. But the point I tried to make is just that like you really cannot store anything global. Like you cannot even store the IDs, so you for sure cannot like know anything about them. But the idea wasn't to say that you cannot communicate with them. So yes, you can, but
Yeah.
So the root log n lower bound works for very specific graphs, right? Not on disjoint paths. Disjoint paths can be solved with constant function with the local model.
Yes. Okay, now I understood the question. Yes, so I was cutting corners a bit, but the idea is that if you have these paths, what you do is that you kind of create a virtual graph around them. So the path is kind of just between two nodes, and it doesn't matter which nodes in the graph, and then you do some magic around them, but the local model just tells you that there are these two nodes. Like you will find two nodes in the graph, that the graph might be complicated, but there are these two guys, and then you can kind of, in this MPC, you can create virtually this complicated graph around these guys. But I didn't want to go too much into that, and actually the lower bounds are usually like tree-like. So they are not so difficult. They are usually regular and tree-like, so actually they are pretty simple. So, but I didn't want to say anything about that because it somehow is besides the point. Maybe, I mean, maybe I confused everyone because of that, I don't know.
Okay, one more. Do you have a question?
Those graphs, I think, are not really regular. Even the cluster.
Well, they look regular around the nodes, right? I mean, everything looks very similar to the nodes.
Sure. The neighborhood.
Yeah.
It's not regular.
Yes, I mean, okay, with the matching not, but with almost all the constructions that you can find, they are pretty much regular. I mean, again, my point was just like, this is not so super important.